Hi, my name is Aaron Johnson. Welcome to Microscopy Society of America webinars. Today's webinar is TEM to STEM, the Scanning Transmission Electron Microscopy Revolution. This is a two-part webinar. Today's is a presentation. Tomorrow, Thursday at 2 Eastern, is the demonstration. Some rules for today. Please keep your mute on during the presentation. If you have a burning question, you can pop that into the chat function. I will record those questions in order of receipt, and when we get to the Q&A, the question and answer period, I will then present them to our speaker. With that being said, our speaker today is Nick Rudowski. He's from the Nanoscale Research Facility at the Herbert Warrenton College of Engineering at the University of Florida. His webinar today, From TEM to STEM, the Scanning Transmission Electron Microscopy Revolution, should be enthralling. With that being said, I'd like to welcome Nick. Nick, the floor and the wheel are yours.
Okay, thank you, Aaron, for that wonderful introduction. So today I'm going to be talking about something that I termed to be the scanning transmission electron microscopy revolution. So if you stay tuned, we're going to learn about what this is and what it all means. Okay, let's make sure I can advance the slides. Okay, make sure the hide meeting controls. Okay, so just to start with acknowledgements here. So of course, MSA for this wonderful opportunity. My facility where I work at the University of Florida, which I will note is renamed from what it was when I did this the webinar back in May. We are now the Nanoscale Research Facility instead of the Research Service Centers. I want to acknowledge the manufacturers of the microscopes that I use, Thermo Fisher and Joel. Thermo Fisher, of course, being formerly FEI. And of course, my wonderful family here. And these are the same pictures I showed in my previous webinar. This is the three of us, the human components at my brother-in-law's wedding. And of course, what would I be if I didn't show, my non-human family members? So there's my dog taking a nap in my lap and my cat in a laundry basket daring me to move her. So now that we have the acknowledgements, so we're going to see quite a bit of simulations here of diffraction patterns. And so I want to share with you where I got this information, where I did the simulation. So this is using a software package called MuSTEM. The most recent version is 5.3, and it's based on this publication right here. And there's a link down there at the footnote for the slide where you can actually get this and you can run it yourself. It is freely available and you can use it yourself. It is fairly easy to use and you can use it to simulate lots of different STEM data. I used it specifically here to simulate what's called position averaged seabed patterns, which we're going to see a lot of today. And so these were all done using this MuSTEM package. All right, so here's the outline. So we're going to start by discussing TEM versus STEM, the configuration of the microscope, how we form the images, and critically here, the role of the diffraction pattern in all of this. Then I'm going to give you a brief history of STEM, which is a rather sordid tale, as you might think. And we're going to see actually a rather interesting graph where I plotted the resolution of STEM over time. And then we're going to get into the meat of this, which is the different imaging modes for STEM and the different perspectives. We can see this both in terms of reciprocal space or delta K space, and we're going to see lots of applications and examples. So TEM versus STEM. So if we start by looking at TEM, if we boil TEM down to its essence, this is all that it really is. Okay, so obviously there's more to the microscope than just what I'm showing here, but if we boil it down to its essence, we're starting with a crystalline sample, presumably. We're illuminating it with a parallel incident beam, which is spread out over some area. The beam interacts with the sample, and we get Bragg diffraction, and some of the electrons exit the sample with no net change in direction. We call those direct electrons. Then if we have a twin objective lens design, we have a post field for our objective lens that then focuses the exit wave from the sample into an image. And along the way, we form what's called a diffraction pattern at the back focal plane of the objective lens post field. So the diffraction pattern is where all the rays coming from the sample traveling in the same direction are focused to the same point. and that's where we see the diffraction pattern. So at the same plane, we also put what's called an objective aperture. So using this, we can select what part of the diffraction pattern contributes to our final image. So if we look at an example of this, so I maintain, if you've watched any of my videos, that silicon studied along the 110 zone axis is the most studied zone axis by STEM ever, probably by high-res TEM, of course. And so here's a high-res TEM image of silicon along this zone axis, okay? And so what you're seeing here are what are called lattice fringes that result from interference between the Bragg and direct components of the exit wave. And of course, also you can have interference between Bragg components, but usually for simplicity, we just consider the interaction between the Bragg and the direct. There's a phase difference that gives us what's called phase contrast, and that's why we see these lattice fringes, okay? But the key point here is that STEM images are a parallel acquisition process where all the pixels in the image are acquired at the same time. And then there's a nice equation here. If we're considering specifically high-res TEM, which is what we're showing here, there's an equation for the resolution as a function of the third-order spherical aberration coefficient and the wavelength of the electrons. The key point here is actually the 0.66, though, in front. Because as we're going to see, there's an equation very similar for STEM, and that coefficient is a little bit different. So now if we look at the case of STEM, so now we're using the pre-field of the objective lens to focus the incident beam to a point on the sample, or what we call a probe. And we characterize that probe primarily using what's called a semi-angle of convergence, alpha. And this is a key parameter in any type of STEM imaging, as we're going to see today. And so if our sample is, again, crystalline, we end up with a diffraction pattern that comes out the other side of the sample. And just like we had before, we have Bragg and direct components. But because we have a converged beam, we don't see focus spots anymore. What we see are actually disks. Okay, so our diffraction pattern becomes what's called a convergent beam electron diffraction pattern, or a seabed pattern. Okay, so we're now doing this at a point or a pixel within an image, and so we have to move the probe around at each pixel within the area that we're imaging, and so we're forming a seabed pattern at every single pixel. That seabed pattern at a given pixel is being projected onto a STEM detector. Now, I've shown just one STEM detector here, and this would be what's called an annular detector, but you could have more than one detector. You could have a detector that's just a circle. You could have a detector that's actually in segments. I'm just showing one here that's annular, just for simplicity. The STEM detector then converts that seabed pattern into a signal, and it maps it for that pixel, okay? And that does this pixel by pixel. So if we again go back to silicon along the 110 zone axis, but now we're looking at a HAADF-STEM image. Okay, so this is the acquisition process. So this is done now in series, one pixel at a time. So you can see that this image is not completely done. It's about halfway done. And now here's the equation for resolution in STEM mode. So you can see the equation is very similar to what we had for high res, but now the coefficient in front is 0.43. Okay, so you can look at that and say, well, it looks like my resolution in STEM is actually a little bit better than it is in high res. Okay, and that's actually true. The other thing too is that we could rearrange this equation in terms of alpha. Okay, in terms of what's called an optimal value of alpha. So the higher we can make the optimal value of alpha, the smaller our resolution. And the way that we do that is using CS correction usually. Okay, so no matter whether we're talking about TEM or STEM, it's always about the DP when we're talking about the images that we form. Okay, so it all comes down to the DP. So in TEM mode, we're getting focus spots in the DP, which we usually call selected area diffraction pattern. We use the objective aperture to select the part of the DP that contributes to the final image. In STEM, we have a focused converged beam. The DP then becomes disks, which you can think of as magnified spots from the SADP, which is the seabed pattern. The diameter of the spots increases as I increase alpha. We get a seabed pattern at each pixel, projects onto the STEM detector. Detector converts seabed pattern to a signal in the image, goes to the next pixel and repeats. Okay. Now, one thing that we can define, if we're scanning the probe over an area, the seabed pattern that we're going to observe, if we actually look at our viewing screen, is going to be position averaged. okay? And we call that a positioned average seabed pattern or a packbed pattern. So that's a common term that you will see associated with STEM. So if we look at a comparison of a selected area diffraction pattern versus a packbed pattern, again, for silicon along 110, and again, these are simulated, so we have the case here where alpha is approximately 0. So I didn't make it entirely 0. The reason I didn't make it entirely 0 is because if you simulate this with MuSTEM with 0, your spots end up being single pixels, and they're very difficult to see, okay? But you can still see, right, at 0.3 millirad, which is probably not unreasonable. In fact, you might use a slightly larger version this or a slightly higher value of alpha than this when you're actually doing high res. But the direct spot is indicated here. One of the things you'll notice, right, is that it's not the brightest spot in the pattern, and this can often be the case depending on the nature of the sample and when you account for dynamical effects. But that corresponds to delta K equals 0, meaning there's no net change in direction of the electrons after they leave the sample. So now if we increase alpha to 10 millirad, okay, so this is literally the same sample, same orientation. I just increased alpha to 10, okay? So my spots, right, enlarged into disks. And we can see that there's a lot of overlap now between the disks in the pattern, okay? So we have a direct disk and then we have Bragg disks. So if I go back to the previous pattern, you can see each of those focus spots is actually at the center of a Bragg disk or a direct disk, okay? So again, that's the previous, that's the focus spots, that's the Bragg. Okay, so 10 millirad, this is typical of what we would use if we're doing non-corrected STEM imaging at atomic resolution. You can think of these spots as you can think of the disks in packbed as magnified SADP spots, if that's helpful. Okay, so if we look at this alpha parameter in a little more detail, again, it's silicon along 110. So if we increase alpha to 2 millirad, we can see the spots get bigger, but I'm not overlapping yet the disks at all. If I go to 10 millirad, as we just saw, right, now I'm getting a lot more overlap. And if I go to 22 millirad, so this would be typical of something where we're doing like CS corrected STEM. We're using alpha values typically around 20, 22 millirad, maybe even a little bit higher. I'm getting even more overlap, okay? So the disk diameter and overlap increases with alpha. We also increase, if we can increase the optimal value of alpha, we're going to improve the resolution via CS correction, which is why we would use a value like 22 millirad. But depending on what our application is, we may not actually need to do that. So more isn't always better. Better is better is a common phrase, right? So depending on our application, we may actually use a value of alpha that is much less than optimal. Okay? It depends on the STEM imaging mode. So now, if we look at our objective lens, it has a twin lens design typically, which means that we can think of it as having a pre-field and a post-field, and the sample sits approximately in the middle, okay? So there's a upper pole piece and a lower pole piece, and in the upper pole piece, we also have what's called a mini condenser lens. So we can manipulate all these lenses to get a desired illumination condition for the sample and also the actual environment of the sample, as I'm going to explain here in a minute. So for instance, if we strongly excite the objective lens and we turn the mini condenser off, we can get a large alpha value and presumably a fairly small probe, okay? If we were to keep the mini condenser on, we could make the value of alpha much smaller. And another thing we could do is we could turn off the objective lens entirely, okay? So the reason we might want to do that is if we're looking at, say, magnetic domains in the sample, and we don't want to alter the domain structure because the objective lens field strength is actually very strong where the sample is. It's about 1 Tesla, okay? So that's obviously enough to potentially alter a domain structure. So there's a lot of flexibility here with what we can do as far as the illumination. And then if we go to the actual STEM detector, the important thing here are what are called collection angles. And so every STEM detector has 2 collection angles, an inner and an outer. In this case, I'm showing you what's called an annular detector, where there's a hole in the middle. And so if we draw a vector from the middle of the detector to the inner rim and the outer rim, so that distance to the inner rim corresponds to the inner collection angle, and the distance to the outer rim corresponds to the outer collection angle. Obviously, if I didn't have a hole in the detector, then my inner angle would be 0, of course. Okay. So then we project a seabed pattern onto the detector, right? Because we can't change the size of the detector, but we can alter the size of the seabed pattern that's being projected onto the detector. So what we see here is that I'm not magnifying my pattern a whole lot, and as a result of that, my collection angles are actually quite large. Okay, large, of course, being kind of a relative term in STEM. I think the inner angle here would be something around like 50 millirad, which is really only about 3 degrees, but that's actually quite large in terms of STEM. But if I increase the camera length, right, I increase the magnification of the pattern, and now my collection angles have gotten a lot smaller. So you can see now in the previous version, I'm not really collecting any direct or Bragg electrons, okay? I'm collecting just the background. But now I'm actually collecting direct and Bragg. Okay, I have parts of those that are actually falling on the detector. And then if I increase the camera length even more, I'm detecting even more of that direct disk. And again, also the Bragg electrons or the Bragg disks as well. Okay, so when we show diffraction patterns, we typically use reciprocal length units, but we also like to think in terms of angles. Okay, so if we want to convert those to an angle, we can use this simple equation here. So we multiply delta K by lambda. Make sure, of course, you're in nanometers in one and reciprocal nanometers in the other, and you get your angle for beta out in radians, which you then need to convert to millirad. So 17 millirad is about 1 degree, just to give you an idea. Okay. So again, we can manipulate the camera length to adjust the collection angles as we desire. And then, of course, last but not least, is the sample itself. Okay. So lots of variables here. What's the crystal structure? Okay. We got 3 different crystal structures here, for example. Okay. How thick is the sample, right? I've got the probe here impinging on the sample along a direction. How thick is it going through, right? That's obviously critical. And then what's the orientation of my crystal, right? So this is strontium titanate, and we're looking at 3 different zone axes here, okay? And this, of course, is not exhaustive. There's other variables we could account for, but these are some of the critical factors in the resulting STEM images. All right, so now we're going to go over a brief history of STEM. And so I want to give credit where credit is due. There's a great textbook that's actually dedicated to STEM. I don't believe that there has been a second edition of this come out yet. This is from, I believe, 2011, so it's actually 13 years old, but it is dedicated to STEM. It talks about theory, talks about applications. It is great. And chapter 1 is an exhaustive 90-plus page history of STEM. Okay, so I highly encourage you to check this out if you want more than just the cliff notes I'm going to give you here. But these are some of the milestones here. So back in 1937, we got the very first STEM of any kind developed. Okay, it was developed in Germany, and sadly, it was destroyed during World War II. And then it took about 30 years for there to be another advancement, but the STEM that was equipped with a FEG was developed, and we got a big bump in the resolution. Okay, so about an order of magnitude improvement. And then a few years later, we got another increase in the resolution by improving the objective lens design, and about, again, a factor of 10 improvement. In 1971, we first coined the term Z contrast, where we were where high Z atoms on a carbon support were being imaged. And then in 1974, the first atomic resolution HAADF-STEM images were shown. Okay, and these were small crystallites and single atoms, and we were approaching 2.5 angstrom resolution. 1978, there was a paper that was published that explained why we see lattice contrast or atomic resolution contrast in STEM images, which was actually due to seabed disk overlap. In 1979, we have the first experimental HAADF-STEM investigations. In 1984, this was the first atomic res STEM imaging of large single crystals, right? So this would be like a silicon wafer, for instance. And then in 1987 to 89, these were the first multi-slice simulation of STEM images. And so multi-slice simulation approach, this is actually what MuSTEM uses, and this is routinely done now and is critical actually in understanding STEM data. In the 1980s, actually, the first atomic resolution STEMs were commercially available from a company called BG Microscopes, which is no longer in existence. And then in 1989, we saw the first Z contrast images of semiconductors. The resolution was about 2.2 angstroms in silicon germanium. And then in 1989, the 2 angstrom resolution barrier was demonstrated in YBCO superconductor. In 1990, the robustness of HAADF-STEM was demonstrated, and I'm going to explain what that means in a little bit greater detail here shortly. And then in 1993, for the first time, the silicon dumbbells along 110 were resolved. Okay, so that's about 1.3 angstroms, which was at 300 kilovolts. In 1997, this was the first time CS-corrected STEM was demonstrated. Okay, so this wasn't sub-angstrom the first time it came out, but it was about 2.2 angstroms. 1998, Joel came out with the 2010 F-STEM, which became very popular and was commercially available. And depending on the pole piece you got, could have resolution as good as 1.3 angstroms in STEM mode at 200 kilovolts. In 2001, the resolution for CS-corrected STEM was about equal to that for non-corrected STEM. Okay, so at that point, you would think, well, that would kind of be the launching point for CS-corrected STEM to overtake non-corrected STEM, and that's indeed exactly what happened. In 2001, there was another important paper published that talked about the role of the environment of the microscope in getting proper STEM images, specifically talking about things like airflow, magnetic fields, temperature variations. In 2002, the 100 picometer or 1 angstrom barrier was broken for the first time. And in 2003, single dopant atoms were first imaged by CS-corrected STEM. This was bismuth and silicon. In 2004, we had sub-angstrom resolution of crystals demonstrated. This was silicon along the 112 zone axis, which is 78 picometer spacing. In 2006, this was the first time we had 5th order CS-corrected STEM demonstrated, and this was demonstrated in gallium nitride, and the resolution was about 63 picometers. In 2009, the 50 picometer barrier was broken, and so this was germanium viewed along the 114 zone axis, 47 picometers. And in 2010s, we have CS-corrected STEMs commercially available from several manufacturers with sub-angstrom resolution. And this is the last slide, I believe, here. So in 2011, we had a technique was introduced called ABF-STEM, which was shown to be intuitive and robust and allowed imaging of low Z and high Z elements at the same time. In 2012, low voltage CS-corrected STEM was demonstrated, so the ability to get sub-angstrom probes at lower voltages. In 2012, DPC, or differential phase contrast STEM, was demonstrated at atomic resolutions as a way to image internal electromagnetic fields in samples. And in 2015, FEI introduced drift-corrected frame integration as a commercial software package using their Velox software, which works great for routine high-quality atomic res STEM imaging. And then in 2019, the 4D STEM imaging technique was demonstrated. The idea being that you're collecting and recording a seabed pattern at each pixel in an image. So just to give you an idea, this is what the first STEM looked like back in 1937. The resolution was about 40 nanometers. So you can see, not very complicated. Basically, it's a source and 2 lenses and a detector. Okay, that's all that it really was. You can see there's nothing very impressive about the detail that we're seeing, right? Again, 40 nanometer resolution, but this was the start of it all. So of course, very important. And then if we look at actually what was happening at my institution, kind of around the time when this was when I was a postdoc actually. So our STEM resolution was not great here. So this was capable of getting 2 angstrom or less STEM resolution, but the images we were getting out of this were not very good. We didn't have CS corrector on this system for starters, but the room environment for this microscope was terrible. We had exposed AC vents. We didn't have proper thermal regulation. We had stray fields in the room. The chiller for the microscope was actually outside, so you can imagine that we had issues with the cooling water not being properly regulated. So when we actually took atomic res STEM images, they looked terrible. Okay, so this is HAADF-STEM of GAN along 0001, and you can see there's a lot of like ballooning and compressing and distorting of the image. Part of that is due to the sample not sitting still. Part of that's due to the fact that we have the EM fields present as well. This is germanium along 110, and it looks equally bad, okay? So the resolution of these, obviously not good. These images aesthetically not very good either, okay? So then if we flash forward to today, we now have the Themis Z STEM, and you can see this microscope is housed inside of its very own Faraday cage in a state-of-the-art room with all of these environmental factors properly accounted for. It also has a dedicated magnetic field cancellation unit inside of the enclosure. And so if we open up the door here, we can see this is our microscope now. And so we actually have CS correction built into the column here. And so these are the kind of images that we're getting here routinely now. Okay, and these are, of course, sub-angstrom in detail. And this is strontium titanate along 001, which is something we're going to see a lot of, which has been studied very, very frequently by STEM. And so it's very interesting if you actually go through and you plot the measured resolution as a function of year. This is the graph you get. So notice on the left, that is a log scale, okay? So if we look here, so this is the first data point from 1938. This is a data point from I believe 89, where the resolution was about 2 angstroms. And then this is what we're getting today in 2024. You can actually regress this, and you get something that looks like this. So it's interesting if you regress this, it's telling us, oh, we should be better than we are right now. So as far as I know, we haven't gotten below the 47 picometers that we have currently seen, although I don't know, strictly speaking, if that's true. But it's interesting to think, is there some kind of a relationship for resolution as a function of time, right? Those of you familiar with electronics, maybe you've heard of something called Moore's Law, which talks about transistors inside of a device, the number changing with time. So it's interesting, do we have something like that for STEM resolution? You would think maybe we get some kind of asymptote at some point. So like, I don't think we're going to get, to 1 picoamp resolution anytime soon, but, we can always dream, can't we? Okay, so today, STEM has overwhelmingly overtaken TEM, okay? It's overwhelmingly used compared to TEM. It has inherently better resolution, as we've seen here, right? Just based on these very simple equations. You have less of an impact from inelastic scattering on the images, right? Because your STEM detector doesn't care, right? When the STEM detector has the electrons hit it, it converts it to a signal, and it doesn't really care if they lost energy or not, okay? So really, the probe being focused on the sample has more of an effect, although not to say that what happens inside the sample is irrelevant, because it's not, because it is, but it has much less of an effect because with regular TEM, we'd have to worry about chromatic aberration. We don't really have to deal with that so much in STEM. We now have CS probe correctors that are ubiquitous and very easy to use, or getting easier to use, so we can get sub-angstrom STEM probes routinely now. And it's routine now to do high quality atomic resolution STEM, okay? Because we have renewed emphasis on microscope and room design, and we now have improved imaging acquisition techniques. And we now have a slew of different STEM imaging modes available. So HAADF was, or still is, right, the most popular, but there's a bunch of other ones, as we're going to see here, okay? And then when we add on to this the analytical capability with EDS and EELS, right, that we can do in STEM mode, and the resolution that we get from that, which is limited mainly by probe size, STEM clearly has overtaken TEM. So then, what am I talking about when I say the STEM revolution? So I call this a paradigm shift. The paradigm shift from TEM to STEM, when STEM started becoming more important than TEM, okay? So this is entirely my opinion, but I'm going to say between 2005 and 2010 was when this paradigm shift occurred, okay? And the reason why I'm going to say that is because we saw a major increase in STEM-related publications, in materials characterization using STEM, but also in theoretical aspects of STEM imaging. We had the first publications on quantitative atomic resolution STEM come out, and these improve the fundamental understanding not just of STEM, but also of TEM2. which is interesting. If you read these, you will learn that. There was also a major shift in STEM manufacturing and design. So STEM performance became a primary design consideration, whereas it was more like an afterthought. So even with the Joel 2010F, when STEM mode was introduced with that, it was really kind of an afterthought to have the STEM mode rather than a primary design consideration. Okay, but now with these microscopes, STEM mode is often the primary design consideration, especially now that you have manufacturers that offer dedicated stems that only function in STEM mode. Specifically, you have Nyan and Hitachi, they offer dedicated CS-corrected stems. So this is what I'm terming the STEM revolution. So now we're going to talk about how we can do STEM. Okay, so the STEM imaging modes. And there's a lot of them. Okay, if you actually look through and do a proper accounting for this, there's many different ways you can do STEM. So there's really 10 of them here, unique ways. So we're going to start with HAADF, high angle annular dark field, because that's still the king, so to speak. And then we're going to talk about what's called false bright field, low angle annular dark field, annular bright field, dark field, and then differential phase contrast, which has 4 subtypes. There's DPC itself, which is a vector field image, which measures seabed pattern displacement. There's integrated DPC, there's charge density DPC, and then there's Lorentz. Okay, so that's 10 different types of STEM modes that we have at our disposal. So before we get to that, I want to introduce this idea of what is a robust imaging technique. Okay, so what makes an imaging technique robust? It has to do with how intuitive the images are to interpret. So in a qualitative sense, how insensitive are the images to certain variables? So 2 of the main ones are the thickness of the sample and the focal state of my lens. Okay, so if we look at high res, because we're seeing contrast from interference between direct and Bragg beams, our high-res image effectively is a wave interference pattern, which is impacted by the thickness and it's impacted by the focus. Okay. As a result of this, our images are not intuitive. We're not seeing a picture of the actual structure, and so high-res TEM is not a robust imaging technique. Okay. And this is, in fact, the main point of the STEM resolution, is the need for more robust imaging techniques. This is what drove the STEM resolution, was this limitation in high-res TEM. So here's proof of this lack of robustness, and I actually showed this very slide when I did the webinar back in May. So this is high res of silicon, again along 110, and so if we project the atomic structure onto the high res image, we can see that it looks nothing like the high res image. And in fact, I don't even know if that placement is correct. I just guessed, but the point is, right, we're seeing interference of fringes, and in this case, it doesn't look anything like the structure. If we look at something that's more complicated like alumina or sapphire, then it's even worse, okay? And you can see very clearly, I have these well-defined bright and darker spots. So you might think, oh, well, that's got to be, columns of aluminum, columns of oxygen. And then when we project the structure, though, it looks absolutely nothing like that, okay? So again, the point here is that this is not a robust imaging technique, and the images are not the same thing as the true atomic structure, but they are related to the structure. And then here's more proof of this. So again, this is high res of silicon, and this is a short video, and you're going to watch what happens here as I change the objective lens. So the contrast in the lattice fringes changes dramatically, and I can actually get the same contrast as I go through a certain amount of defocus. Right, so I'm back to the same contrast again. There, I'm back to the same contrast again. I don't know if I'm under focusing or over focusing here. That's not the point. The point is that the lattice fringes are sensitive to the focal state. Okay, so again, right, it's hard to make heads or tails of this when you have this kind of dependence. Okay, so your fringe contrast changes dramatically with the focus. So with that in mind, we're going to talk about what is easily the most popular and still most important STEM mode, which is HAADF. Okay. So we're going to look at each of these STEM modes from the delta K space picture or diffraction picture. And so here we have simulated pack bed of strontium titanate along 001 with a fairly large value of alpha, like we would use for CS-corrected STEM. And so in this case, we're using an annular detector, and there isn't really a consensus on this, but if you look throughout the literature, an inner collection angle of at least 50 millirads tends to be typical when we're talking about HAADF. So what you notice here is that I'm not really detecting any direct, or well, I'm not detecting any direct, and I'm not detecting any Bragg diffraction either. Okay, so I'm detecting everything that's beyond that. Okay, so I'm detecting a background signal, which is z-squared sensitive, which we call a thermal diffuse or incoherent background. Okay, so one of the things you might notice is, well, this is maybe like a fairly weak signal, and it can be depending on the sample. It certainly is as shown for this sample, but we can still use it to form images. Okay, so if we look at a high res, this is an example. This is high res of silicon, and we have epitaxial growth on the silicon, and there's an amorphous carbon layer deposited on the surface. So we can't really tell where those what those epitaxial layers are from the high res. But if we do HAADF, we can see very clearly that we have a bright layer, and then we have another silicon layer, and then we have an oxide, and then we have the amorphous carbon. So particularly with the oxide, like that was not detectable really with the high res. We really couldn't tell where that started or where that ended, and we can make out the SIGI compared to the silicon on top of it more readily. Okay, so we have the z-squared sensitivity that allows us to delineate the layers more effectively than we would in high res. If we go back to looking at another example of this, which is silicon dumbbells. So again, here's the high res along 110. If we look at HAADF, oops, sorry, and then that's the projected structure. Again, looks nothing like the looks nothing like the lattice image. But if we look at the HAADF image, it actually does. Okay, and then if we project the structure onto the image, it matches up perfectly. Okay, these are the same thing. I changed the color because it looks a little better on the HAADF, but there's no difference otherwise between those two models. Okay, so again, HAADF-STEM is intuitive and indicative of the true atomic structure. And now, what if we have a sample that's a little thick? Okay, so if we have a sample that's 200 nanometers thick, that's really thick. Okay, as far as doing high resolution microscopy, electron microscopy is concerned. And this material is what's called calcium lanthanum sulfide. So if we look at the high-res image of this is along 110 zone axis, the structure is cubic. That's not a very good high-res image. Okay, anybody who's familiar with high-res would agree that's really not very aesthetically pleasing. We're not seeing much detail there. It looks very hazy. That's because we have a lot of chromatic aberration. We're probably getting suppression of the Bragg scattering because the sample is really thick. So not very good. But if we look at the same area with HAADF, my goodness, right? It's like we've put on the, I don't know what's the correct way to say this, right? It's like removing the fog, and we can see perfectly now, right? So we're seeing basically perfect atomic detail here of the structure that we weren't seeing in high res. Okay, and this is again because we're not relying on Bragg diffraction to give us the fringe contrast that we see in high res. Okay, we're looking at a thermal diffuse background that contributes. Okay, so the point here is that if we have a thicker sample, HAADF-STEM is still effective. And then we can also look at things like the polarity in a material. So what I've shown you so far, this has just been single atom materials. But if we have something like zinc sulfide, so this grain here, this light grain, this is zinc sulfide grain inside of a composite material. And then if we look at HAADF-STEM of this grain, so we can see very clearly, I've indicated two zone axes here. Okay, so that's because the zinc sulfide has actually taken on two crystal structures. So there's parts of the grain that are zinc blend, and there's parts that are wurtzite, which is why you see two zone axes there. So we can actually see those in the image, and we can actually see the polarity of the dumbbells. So if you look closely, you can see there's two sets of dots, and one is brighter than the other, and that the brighter one would of course be the zinc, right? Because that is higher Z. So if we actually project this onto the structure, so the zinc being yellow, sorry, the sulfur being yellow and the zinc being magenta, we can actually see the polarity. Okay, and we can actually see the difference in the stacking of the layers as well. So the polarity being that the zinc is facing to the right, if you will, right to the right and up as the along the plane there. The zinc is shown smaller than the sulfur because obviously it's going to have a smaller radius because it is the cation rather than the anion, but it is higher Z. Okay, so we can use HAADF-STEM to directly reveal the polarity. And of course, we must talk about strontium titanate, right? So, along 001, we see bright dots and less bright dots. And of course, we can infer from this that the bright dots are strontium and the less bright dots are titanium oxygen, okay? And so we can directly image the structure of strontium titanate, okay? But there's an important limitation here, right? We have the Z-squared sensitivity, of course, but what happened to the oxygen, right? We're not seeing any of the oxygen here. So this is a limitation, right, with HAADF, okay? This is something we're going to come back to in a little while here. So with the HAADF, it's important to consider the variables that are incorporated into this, and one of them is orientation sensitivity, okay? So depending on how the beam travels through the material, that's going to impact what we see. So this is true at a fairly coarse scale, which this would be micro scale, of course, right? So again, and this is calcium lanthanum sulfide. So all of these grains are the same composition, okay? But they're oriented differently. So some of them are brighter than others, right? And the ones that are brighter than others are ones where you probably have stronger channeling of the electron beam through the grain, okay? So this is kind of a hack for those of you who do HAADF-STEM imaging. If you look for an area on the sample that's a little bit brighter, it's probably closer to a zone axis than an area that's not, okay? Because it's going to channel more strongly, okay? So the brighter grains mean stronger channeling of the incident beam. And this is true down to the atomic level as well, okay? So again, if we look at HAADF of strontium titanate along 001, if we're at 0 millirad off of the zone axis, we're going to see the best detail we could ever hope to see, right? Those atomic columns are going to look really sharp, really well defined, just like we're seeing here. If we tilt off 10 millirad, okay, so basically I've tilted the sample down, right, toward the negative y direction, about 10 millirad. And so we can still see the columns, but I think we can agree that's probably not as sharp as what we were seeing on the left, okay? So 10 millirad, that's almost 2/3 of, well, it's less than that. It's less than 2/3 of a degree, okay? But if we go to 20 millirad, right, so now we're well over a degree, and we can see that this doesn't look very well defined at all, right? So our columns are now smeared out and they don't look well defined at all. Okay, so this is true down to the atomic level. Atomic scale detail is also very orientation sensitive. We get stronger channeling of the beam when it's aligned with the zone axis. We see sharper contrast with better defined columns. And so the point is that we talk about the Z-squared sensitivity of HAADF, but it's more than that. Okay, we also have to account for how the beam travels through the sample, and that's where we have to account for the channeling. Okay, so just to summarize HAADF, it is the most important STEM imaging technique today still. Robust intuitive images, representative of the true structure. It's easy to configure, right? Very easy. You just need an annular detector, make your camera length short. You don't need any sort of special image processing. You have the Z-squared sensitivity as well as the orientation sensitivity. If your sample happens to be on the thick side, you can still usually get usable information from it because the energy losses inside the sample are basically irrelevant. But not so fast, right? We did see an important limitation, okay? And that important limitation is light elements, okay? So the Z-squared sensitivity is a blessing, but it's also a curse, okay? So if we're trying to see light elements in the presence of high Z elements, that's going to be a problem, okay? And there's also, right, a potential signal to noise issue. So if you go back and you look at the diffraction pattern projected onto the STEM detector, what you'll notice is most of the intensity in my pattern is low angle scattering with the direct and the Bragg components, okay? That's where the majority of my signal is, okay? So if my sample happens to be really thin, the HAADF signal is going to be very weak, okay? Or also it's going to be very weak if I have a low beam current, right? If I'm trying to do like low dose imaging, I'm trying not to, cook the sample. If I try to do HAADF with that, I'm going to get probably a pretty poor signal to noise, okay? So those are two important things to consider, and these actually lead us to additional STEM modes, as we're going to see here. Okay, so from this, we're going to transition to what I call false bright field, and I will freely admit that I came up with this term, false bright field. The majority of the literature simply calls this bright field, but I don't agree with that, as you're going to see here later on. I prefer to call this false bright field to delineate it from true bright field, as we'll see a little bit later. Okay, so again, if we look at the pack bed picture, so we're using a circular detector. The inner angle, of course, is going to be 0, and the outer angle is going to be less than alpha. Okay, so based on what I have here, I have overlap of my direct and Bragg disks that are contributing to the STEM detector. Okay, and so this is what I'm detecting now. I'm not detecting thermal diffuse scattering anymore. I have a direct disk and overlapping Bragg disks that are collected. Okay, so if I look at the effect of this now, so false bright field STEM, okay, so as a result of the fact that I'm now collecting direct and Bragg electrons that overlap and interfere on the STEM detector, I'm now going to see sensitivity to things that I didn't see before. And one of them is the focal state. Okay, so this is the under focus state. And you can see that it really doesn't look anything like the structure of strontium titanate. Okay, not at all. If I look at the case where my focal state is 0, so this would be optimal focus for HAADF. Again, does it really match up? Not entirely, right? Really not anything close, okay? Now if I go to an overfocus state, it looks different still, okay? So it looks completely different in all three of these focal conditions, okay? So we see contrast reversals with changing in focus state. And this is again due to the fact that we have phase contrast between the direct and the Bragg beams. So what we're doing when we do false bright field is essentially high-res TEM in STEM mode. Okay, the images are not intuitively interpretable as a result. Okay, so again, just to summarize, false bright field is essentially high-res in STEM mode. Okay, again, because we're seeing contrast due to interference between the direct and the Bragg disks, we're looking at coherent scattering and phase contrast. So we have the same limitations that we have with high res. We would see thickness having a qualitative impact as well, even though I didn't show it, but the imaging is not robust. Okay, there are several ways to configure this. You can do it actually, in addition to having a circular detector, you can do it with an annular detector and an objective aperture. Okay, you don't need any special image processing to do this, but I think without question, this is probably the least useful STEM mode for practical applications. So if you're trying to analyze a specimen, right, this really isn't going to help you much, okay? Where this has value, though, is for doing fundamental theoretical investigations of about STEM, okay? And actually, this is one of the papers that actually did this. Okay, so we're going to transition here to what's called low-angle annular dark field. And again, here's the pack bed picture. So now we have silicon with a semi-angle of convergence of 10 millirad along 110. Okay, so now my inner collection angle is slightly larger than alpha. Okay, the outer collection angle, is typically going to be about 4 times that based on the typical dimensions of the annular detectors. Okay, but the key point here is the inner angle being slightly greater than alpha. The point here, though, is we do not want to detect any direct component. Okay, so we're detecting Bragg disks, and we're also detecting a thermal diffuse background. So you can think of HAADF as a Bragg component that has been added on top of a HAADF component. Okay, so if we look at an example of this, of silicon dislocation loops, okay, so this is what the HAADF-STEM image looks like. So my dislocation loops, right, there's a strain field associated with those, okay? And so that strain field shows up in positive contrast in HAADF, okay? So those loops light up and they become bright compared to a dark background. If I look at the HAADF case, though, I see a reversal of the contrast, okay? So the strain fields show up as well, but now they're in negative contrast, okay? So the dislocation loops then become negative, okay? So in HAADF, the strain fields are positive, and HAADF, the strain fields are negative in terms of the contrast. If we look at something at a little more high resolution, so we're looking at a grain boundary in calcium lanthanum sulfide, Okay, so again, we see that the grain boundary is in positive contrast because it's a lattice image. And again, this is approximately 111 because of the nature of the grain boundary, we don't have perfect zone axis alignment. If we look at what's happening at atomic detail within this area right here, though, so we can see very clearly that grain boundary, even at atomic resolution, shows positive contrast. And then we can see in the areas above and below the boundary, I see kind of blurring of certain parts of the atomic level detail, which is again, right, like we saw with the STO, because you have deviation from the zone axis, okay? So with a lattice image, we can still get, because we have the HAADF component that's contributing, right, we can still get that component in the images, right, which is used for that intuitive interpretation of the crystal structure, but we're adding in the Bragg component as well. Okay, so we have positive contrast at the boundary. In this case, we have blurring of the columns because of the crystal tilt. Okay, so just to summarize lattice. So the main application, in my opinion, is as a strain field contrast enhancement technique. Okay, so in lattice, you're going to have positive contrast from strain fields. The only caveat to that, there's a great paper about this, which you can see below, is if your sample is very thin. If your sample is very thin, then lattice is actually going to give you negative contrast, but by and large, it's going to give you positive contrast. HAADF is always going to give you negative contrast, regardless of the thickness, but regardless of, like HAADF, it's very easy to configure. Okay, you can use the same annular detector. You just have to increase your camera length accordingly. Okay, I do want to state, because I think this is a myth that some people have, is that lattice-STEM is required to observe strain fields. Okay, or specifically the contrast from strain fields, and that is simply not true. Okay, so the truth, of course, is because we have to account for channeling effects, both lattice and HAADF are strain sensitive. Okay, this is predicted by simulations, as you can see below, and as we just saw, right, with the example of the dislocation loops in silicon, this is also confirmed readily experimentally. All right, so now we're going to move to true bright field, as opposed to what I specified before as false bright field. Okay, so what we have now is an experimental packed bed picture. So the ones I showed you up to this point were all simulated. This is an experimental packed bed picture from aluminum scandium nitride, which has the Wurtzite structure. You can see I've indicated two zone axes here because that's actually what's contributing to this packed bed pattern is two different zone axes over the area on the film that's being scanned. And you can see my semi-angle of convergence is now down to 1 millirad, okay? So I'm seeing a lot of separation of the spots, okay? So if I want to form a true, so now that I have separation of these spots, it's very easy to select only the Bragg disk, okay? I don't have any overlap with any other disks, and I can isolate this perfectly, okay? So my inner angle is going to be 0. My outer collection angle is going to be a little bit bigger than alpha. Okay, so again, I have to reduce alpha to separate the disks, and then I'm only going to detect the direct disk. Okay, so if we look at what this looks like, the AlScan, which is grown on 0001 silicon carbide. Okay, so again, we have variable zone axis orientation for the AlScan, which is grown on the silicon carbide. Above the AlScan, we have a layer of chromium, which was evaporated as part of the lamella prep process. But we see inside of the AlScan, we have areas that are darker than others, and those would be areas that are diffracting more strongly than others. Okay, so the AlScan, of course, we would expect to have uniform composition over the thickness, and because this was a lamella prepared via dual beam fib, we would expect relatively constant thickness over the from top to bottom of the film. So we don't expect there to be any composition or thickness variation. So what we're seeing here is basically only due to diffraction contrast. Okay. That's not to say you couldn't also have mass thickness contrast. So if, for example, we could do the thought experiment, what if everything in here was amorphous? Okay, if the chromium, the AlScan, and the silicon carbide were all amorphous, those would have different grayscale values because those would have different mass thickness contrast. But because those are all crystalline and they diffract, that's a contributing factor. So we're seeing that contribution as well. And that tends to, in many instances, overwhelm the mass thickness component. Okay, so we can look at another example of this. So aluminum magnesium alloy, which has a bunch of dislocations in it. So this is a low mag image of a single grain. And as a result of the lamella prep process, there's a lot of bending within this grain, okay? So you're seeing the result of that bending in this bright field stem image. So what you can see is that the appearance of the dislocations is highly variable depending on where I am within this area, depending on how much bending I have, okay? So what we can actually see is that where I'm closer to a Bragg condition, I have less sharp contrast of my dislocations, okay? Where I'm a little bit more deviated, my contrast becomes a little bit sharper. So if we actually look at this area right down here, we can see this transition really well, okay? So we can see it really very clearly. So over on the right, that's where I'm transitioning away from an area that, or I'm closer to an area that is near the Bragg condition. So my dislocations do not look as sharp in terms of the contrast because I'm getting a contribution or more of a contribution from the non-dislocated background. But as I transition to the left, my dislocations become sharper and well-defined, okay? Because I'm deviating more from the Bragg condition. But I don't know what Bragg condition. That's an important part to specify here. So just by doing bright field alone, I don't really know anything about what the Bragg condition is, okay? Assuming I just put it in there and I select the Bragg disk, okay? So the strain fields exhibit negative contrast. It's deviation sensitive. Okay, so bright field stem, this is the analog of bright field TEM. The advantage though, right, as I specified before, is the effective inelastic scattering is much less detrimental, okay? So if you had a thick sample, doing bright field stem is probably going to be much better than doing bright field TEM, okay? Again, very easy to configure. If you don't have a circular detector, you can do it with an annular detector and an objective aperture. Your primary contrast mechanism is going to be diffraction contrast, with darker being stronger diffracting, but you're not isolating the Bragg contributions usually. It is strain sensitive as well. The strain field is also going to be a negative contrast. These are going to be sensitive to how you're deviated from Bragg's law. Okay, and then you also can have a contribution from what's called mass thickness contrast. Again, darker is going to be higher mass thickness, which will be a negative contrast. You can have both of these present at the same time. Generally speaking, if you're dealing with crystalline materials, diffraction contrast maybe swamps out the mass thickness component, but both of these can be occurring simultaneously. And then if we look at the twin to bright field, or evil twin to bright field, this would be dark field. Okay, so notice I didn't say annular dark field, I said dark field. Okay, so again, same packed bed pattern we just saw. Okay, but now because I have these disks well separated, because my alpha value is 1 millirad, I can select a single Bragg disk. Okay, so same detector geometry I had before, I've just shifted the pattern so that a Bragg disk falls on the detector. Okay, so again, I have to reduce alpha to separate the disks, and I'm only getting one Bragg disk collected. So now if we look at how this looks on the AlScan grown on 0001 silicon carbide, we can look at the bright field and we can compare it to 3 different dark field images. Okay, so over on the right, you see the pack bed pattern, and you can see the disk that is being isolated. Okay, so right now, that's the bright field image. I'm isolating the direct disk. Okay, again, this is schematically what we're seeing, where the substrate starts, the AlScan starts, and where we have the chromium. Okay, and so this is the image isolated from the 0002 reflection from the AlScan. Okay, so what this tells us is that we have a lot of texturing of the AlScan along with 0002 planes. Okay, so those planes tend to be aligned with the growth direction of the film, which is normal to the substrate, okay, based on how we see the seabed pattern. If we look at one of the Bragg deflections that is parallel to the growth plane, so in this case, this would be the 112 bar spot, so we can see that we get different parts of the film to light up. Okay, so we can infer from this which of the zone axes we are aligned with. So which of the zone axes dots to 0 with 112 bar 0? Well, it's 1 bar 0 0. You can verify that. So the areas that are lighting up here are going to be areas on the film that are more strongly aligned with the 1 bar 0 0 zone axis for the L scan. And then we can do the same thing with the 1 bar 0 0 spot. And from this, we can determine which areas on the film are now aligned with the 2 bar 0 zone axis of the L scan. So basically, this is kind of like a texture analysis tool in a way, right? So we can see we have much more of this orientation than we have of this orientation. Again, this is the in-plane orientation, the zone axis that we're looking into the page or out of the page as it would be. Again, we're getting diffraction contrast from single spots. So this is analogous to dark field TEM. So just like with bright field, this is the analog of dark field TEM. The main advantage being that we don't have the effects of inelastic scattering being as detrimental. Again, very easy to configure. And now we only have diffraction contrast, but the real advantage of this is that we're isolating the contribution from a specific Bragg spot. So we're actually seeing the piece of the bright field puzzle, if you will. So we can actually determine, like, okay, which part of that dark area in the bright field is from a certain Bragg diffraction, okay? So brighter means stronger diffraction, positive contrast. We saw how we could use it for texture analysis. It is also strain sensitive. Strain fields are going to give positive contrast, even though I didn't actually show that here. Again, it's going to be sensitive to deviation from Bragg condition. All right, and now we're going to change gears a little bit here and talk about annular bright field. Okay, so we're going to go back to strontium titanate with a high semi-angle of convergence, and we're going to go back to an annular detector. Okay, so the setup here is that my outer collection angle is going to be just under alpha, and my inner collection angle is going to be about half of my outer collection angle. Okay, so I'm getting direct electrons and Bragg electrons that are falling onto the detector. But you can see I have that circle cut out of the middle. Okay, so this is very much an annular detector. Okay, so those are my two main components. And so what we can see is by doing this, it now becomes possible to detect light elements in the presence of high Z elements. Okay, so if we look at HAADF here along 001, well, we can't see the oxygen columns, okay? They get swamped out by the strontium and the titanium oxygen, again, because you have Z-squared sensitivity, right? Which I said before was both a blessing and a curse. But if we look at ABF instead, okay, so now we have negative contrast, meaning the atoms look dark against a bright background, but we can see now we have two sets of very dark spots, but in between those, we actually now see a lighter, a slightly less dark set of spots, and those would be the oxygen columns, okay? So we can actually now visualize the oxygen columns by using ABF-STEM, okay? So again, we can get all three of these elements, which have very different Z's, direct observable at the same time using ABF-STEM. Okay, so this overcomes one of the big limitations of HAADF-STEM, which is seeing low Z elements in the presence of high Z elements. In fact, it's been demonstrated you can image hydrogen in the presence of yttrium, which is pretty amazing because that is a major difference in Z. That's a plus 39 Z difference. The other thing too, if we go back to the packed bed pattern, so we're collecting very strong signals when we do ABF. Okay, we're collecting direct and Bragg signals, which are very strong. So that takes advantage of, so we can take advantage of that if we're doing like low dose imaging, we're using low beam current, that can be very useful, okay? Because otherwise, if we were to collect a HAADF signal, it's going to be very weak, but the direct and the Bragg signals obviously are going to be very strong, okay? So we get very high signal to noise with ABF. We do have robust intuitive images. The reason behind this is, again, because it is annular in nature. Okay, if you want a deep dive into the physics behind it, you can go look at this great paper by Findlay in ultra microscopy, and he delves into the whole thing. Okay, and again, this is fairly easy to configure. It's a little bit trickier than ADF, but still possible to do if you have a single annular detector with an objective aperture, and we don't have to do any type of special image processing either. Okay, and so last, we're going to talk about differential phase contrast imaging. Okay, and which has 4 subtypes. Okay, so DPC principles, the idea here is that when I take a probe and I illuminate it on the sample, if that sample has an internal electrostatic field or magnetic field, it's going to result in a shift in the seabed pattern as it goes out the other side of the sample, okay? Because that field is exerting a force on my probe, okay? So what we can see here, right, is my seabed pattern has shifted a little to the right, okay? So if I have a special type of STEM detector that's cut into quadrants, right? So now I have a segmented STEM detector, okay, that has 4 quadrants, A, B, C, D, okay? So you can see based on how the seabed pattern has shifted, I'm going to get more signal on A than I am on C, and my B and D are probably going to be about the same. So based on that, I can determine that the seabed pattern has shifted to the right, okay? So this is a way of measuring the seabed pattern shift. Okay, that's the basic idea behind DPC, is you're measuring the shift of the seabed pattern as the beam goes through the sample. Okay, if we look at this from the standpoint of a magnetic field, okay, so think back to your physics, right? Force from a magnetic field on a charged particle is QV cross B. Okay, so use my mouse here. This is my sample here, magnetic field is oriented as you see with these arrows. If my direction of travel of the electrons is down, okay, so V is down, but I have to multiply it by Q, which is negative. So QV is going to point up. So then I do QV cross B, okay, so that's going to give me a force that's pointing to the left, okay. So what we should see is a deflection of the beam to the left. So I hate to say this, but I think this diagram from Velox is a little bit inaccurate. I think these discs should actually, this should be actually shifted to the left. This one should be shifted down, and this one should be shifted to the right, again, because of QV cross B. But right, that's the point here, okay, is that we can use this also for magnetic field, same idea. Okay, but the idea is we have a segmented detector. We can measure differences in signal on those segments to measure the seabed pattern shift, again, due to internal electrostatic or magnetic fields. Okay, so if we look at the packed bed picture here, okay, so we have a segmented detector. This could be oriented however you want. I just have these, rotated off by about 45 degrees here, but we have opposing segments here. So the only stipulation here is your inner angle has to be greater than alpha and your outer angle has to be less than alpha. So depending on the type of imaging you're doing, we may want to use a shorter or a higher camera length. Okay, so if we were doing something that was at atomic resolution, we would want probably a higher camera length where my outer collection angle, where the value of alpha would basically take up about maybe 3/5 of the radius of the detector, okay? So it might extend about 3/5 of the radius, okay? If we were doing something with magnetic domains, we would probably want the alpha value to extend a little bit beyond the inner rim here, okay? So we would want to use probably a shorter camera length, right, to do that, okay? So again, depending on the application here, we would want to adjust this accordingly, but these are the stipulations, okay? So we can't have the direct disc going outside of the detector, and we can't have it going inside of the hole, obviously. Okay, so we have 4-segment detector, A minus C, B minus D, to compute the seabed shift. Okay, so what are the types of DPC? So again, if there's a shift in the seabed pattern, that is a vector quantity in delta K space, okay? That is directly related to the magnitude and the direction of the internal field. This vector field can be displayed as an image, and we typically do this using what's called a color wheel, okay? The other way you can do it is actually as a vector field where literally every pixel has a vector in it, and that gets a little, congested to do. So typically what we do instead is we use a color wheel, which I'm going to explain here in a little bit. So then we have DPC STEM, okay? That's what DPC STEM is, where we're displaying a vector field, okay? We're displaying the shift in the seabed pattern as a function of position, okay? Vector as a function of position. So there's a special type of DPC STEM when we turn the objective lens off, which we call Lorentz STEM, because that way we can avoid wiping out the magnetic domains in the material. Okay, so if we consider, for example, an internal electrostatic field E, So DPC is proportional to the seabed pattern shift, which is proportional to the electrostatic field inside of the material. If we then integrate that electric field, we end up what's called integrated DPC. Okay, so what we're doing then, if we integrate that electric field, we end up with potential. Okay, and so this is what we call IDPC, and this is going to give us positive contrast. So our atoms are going to look positive or bright on a dark background. If we differentiate or take the divergence of the electric field, we end up with something that is proportional to the charge density. Okay, and this is what we call DDPC, or charge density DPC, which is going to give us negative contrast. Okay, atoms are going to look dark against a light background. Okay, the advantage of IDPC and DDPC is that these are more linear with Z compared to HAADF, which is more Z squared. Okay, so again, the implication being it's going to make it easier to see low Z elements in the presence of high Z elements. Okay, so if we look at strontium titanate here, okay, so we're going to start with the DPC image. So what are we looking at here? So we're looking at a color wheel representation of a vector field. The idea here is that the vector is denoted by a color and a value for the color. Okay, so if we were looking at red, for instance, the red can go basically from black to peak red. Okay, so black would be the magnitude of the vector is 0, and pure red would be the magnitude of the vector is the highest possible. Okay, so in other words, peak red and peak green and peak blue all have the same magnitude of the vector. Okay, the only difference is the orientation. So the orientation then is dictated by where the color sits on the color wheel. Okay, so based on the color wheel legend in the upper right, red would be pointing straight to the left. Okay, cyan would be pointing straight to the right. Green would be pointing at about a 60-degree angle counterclockwise from the right. Okay, blue would be pointing at about a 60-degree angle clockwise from the right. Okay, hopefully that makes sense. So again, right, we go from black, we can go from peak black to peak blue, right? Again, black would be no magnitude, peak blue would be maximum magnitude. Okay, so this is what we're seeing here. And so then if we take the integral of this and we get IDPC, so now we have positive contrast of the atoms. Okay, and what we can see now is we have 3 sets of bright atoms on here. Okay, so we are now able to visualize the oxygen columns here. Okay, so IDPC allows us to do that, whereas we could not do that before with HAADF. If we do the same thing with DDPC, we can also do this. Okay, so we have 2 sets of dots that are quite dark, and then we have another set of dots that's not quite as dark. But again, because we have more linearity with Z, it's possible to detect the oxygen in the presence of the titanium, oxygen, and the strontium. Okay. So again, DPC tells us the internal electrostatic field down to an atomic level. We do expect that the field is going to increase with Z. So it's kind of hard to see, but actually where the oxygen columns are in the DPC, there is a little there is a little wheel there as well, but it's much weaker compared to the other ones, as we would expect. But the key point here is that if we then compute the IDPC and DDPC, we can now observe the oxygen in the presence of the higher Z elements. We do have a contrast reversal between them, but they both work for that. Okay, and then last but not least here. So if I have a magnetic sample, okay, sample that has magnetic domains in it, iron silicide here, okay, there's a way to image this, which is called Lorentz TEM, to see the domains. If I do that, I can see the domains, okay? So that's what you're seeing here. So those light lines inside of the material, those are the domains between the different, or the domain walls, if you will, okay? What Lorentz TEM doesn't tell us, though, is anything about the strength of the domains and the orientation of the domains, okay? All of that is completely lost in there, okay? So if we switch to Lorentz STEM, right? So again, we have to turn off the objective lens so we don't wipe out the domain structure. If we do Lorentz STEM, we can now assess the domain structure in terms of how the domains are oriented and how strong they are. Okay, So we can see that little triangle on the bottom, that's a red domain. Those are pointing primarily to the left. Um, we have a magenta domain basically on the right. You also notice that there isn't perfect correspondence between the left and the right images. That is because between the left and right images, the sample, I remember, was exposed to the internal magnetic field of the objective lens, and so that presumably, right, altered the domain structure, right, as you can imagine. Okay, so that's why it doesn't look perfectly the same. Okay, but again, we can use a Lorentz stem here to reveal field strength and orientation. Okay, so just to summarize DPC stem, this allows us to image the internal electrostatic and magnetic fields. This is good down to the atomic level. You can see low Z elements in the presence of high Z elements via IDPC and DDPC. This is also a high signal to noise technique. Okay, so again, we're taking advantage of those strong direct and Bragg signals. So this is also another low dose imaging technique, okay, that works well if you're using like a very low current, okay, or you're working on a beam sensitive sample. The images are robust and intuitive. Okay, this is by far though the most challenging mode to configure. You have to adjust those detector segments to give equal response. You do have to process the results to actually compute the DPC, IDPC, and DDPC. So that's part of your software package. So that isn't going to be free. That has to be purchased if you buy Velox, for instance. And if you decide to perform Lorentz stem, well, if you turn off your objective lens, you're going to have to readjust everything, realign everything. There's additional headaches with that. You're going to have to also properly account for how do I get the sample into the microscope without wiping out the magnetic domain structure. Okay, so 2 slides left here. So just to recap, right? So the history of STEM spans nearly 90 years, from 1937 to 2024, and of course beyond. I'm calling the time between 2005 and 2010 when the paradigm shift occurred and STEM became more important than TEM, and this is what I call the STEM revolution. And so I hope you can appreciate from this, right, that HAADF-STEM is really just the tip of the iceberg here, okay? So as we saw, there's 9 other STEM imaging modes, and the point, of course, is that chances are there's a STEM technique that is appropriate for what you are trying to do, what you're trying to study, what you're trying to work on. Okay, so last but not least, if you have any questions about this, you want to learn more, obviously I'm going to answer questions when we're done here. You can please email me. I have a YouTube channel. This presentation, once it's done and recorded, will be posted there, presumably, and you'll be able to see it there. But I have lots of other tutorials, demos, and more. And last but not least, I would like to thank you for your attention and support. And with that, happy to answer any questions that anyone might have.
Thank you, Nick. That was a great presentation. We do have a few questions already popped into the chat. First and foremost for everyone, this is being recorded, and yes, it will be posted posted to the Microscopy Society of America website. And yes, you'll be able to look at it, review it after today. That being said, we have one from Jingtao Ku. Why does the channeling effect make the grain show brighter contrast? I thought if more electron channeled through the specimen without being scattered by the specimen, the HAADF detector will collect less electrons and show darker contrast.
Oh, that's a great question. Okay, so the reason that happens, right, is because the electrons spend more time on the atomic columns. Okay, so when the electrons spend more time on the atoms, they're going to be scattered out to the higher angles more readily. Okay, so that's why you see the areas get brighter when you're aligned with the zone axis more in HAADF. Okay, but I understand what you're saying. Like you would think, well, you're not, right? If you're dechanneling, well, maybe you would think that would be brighter, but actually it turns out to be the reverse. Okay, so when the electrons spend more time on the columns because they're well aligned with the columns, you end up with more signal that way. Okay, so that's the short answer for why you see the brightness increase when you are well aligned with the zone axis.
Thank you, Nick. Next question is from Nima Nikpour Bader. In the Fourier FFT masking reconstruction of HR-TEM images, if we exclude the central spot and apply the mask only on the diffraction spots, frequencies, would the resultant reconstructed image be equivalent to a false BF-STEM image? In both, the central disk is essentially excluded, but the diffracted beams are included.
That's a good question. if you, so I think if you did that, the only thing you would really be doing would be called what's called high pass filtering. I don't think that would be the same thing as just a as a was that specified? Can you actually read that back to me again, Aaron?
Sure. In the Fourier FFT masking and reconstruction of HR TEM images, if we exclude the central spot and apply the mask only on the diffraction spots, parentheses, frequencies, close parentheses, would the resultant reconstructed image be equivalent to a false BF-STEM image?
Okay, would it be equivalent to a false BF-STEM? Okay, so, oh no, that wouldn't be the case, right? So again, with false BF-STEM, you absolutely would want to include that spot in the middle. Okay, so that's the important part of that, right? Is that spatial frequency has to be included. So no, that would not be the equivalent of a false bright field stem. What you're doing if you exclude that direct, or shouldn't say direct, that zero order spot in the FFT, you're doing what's called high pass filtering. Okay, so the information that's around that zero order spot in FFT, that's low frequency information. And so if you remove that, you filter that out. So that's actually a way to filter out noise in the image. But that would not, strictly speaking, be the same thing as forming a false bright field image.
Thank you, Nick. This next one is from Rahu Agarwal. Is it possible to image different atoms in a single phase substitutional solid solution?
That's a good question. So it depends on how the atoms are ordered in the solution. So actually, I can go back here. Bear with me. I'm going to go back quite a few slides because there's an example of a solid solution here that I can show you. Where is it? Okay, right here. Okay, so the silicon germanium is a solid solution. Okay, so this is a solid solution of silicon and germanium atoms. Unless there's some kind of ordering to them, there's really no way to isolate one from the other in terms of knowing where I have silicon versus germanium. The way you can do that is if you have some kind of ordering. So that usually happens when you have like specific, composition with the material. So maybe if you had like, 3 silicons to every 1 germanium or something like that, you might get something like that. I'm not actually sure. I don't know in the case of silicon germanium if you get any kind of ordering. You may not. With intermetallics, I think I know that can be somewhat common with those, but yeah, it all depends on how the material behaves.
Thank you, Nick. Is it possible? Sorry, apologies. This is from Lakshay Shahan. How accurate is two-beam imaging in STEM mode in comparison to How accurate is two-beam imaging in STEM mode in comparison to traditional two-beam TEM imaging of defects?
Okay, so yes, you can absolutely do two-beam imaging in STEM mode. That is very possible to do, especially if you reduce that alpha value down significantly to, like single-digit millirad. You can do that to very good effect, just like you would in TEM mode, and you will have that big advantage of the effect of chromatic aberration inside of the sample being much less of an issue. So yes, the short answer is yes, that can absolutely be an effective way to image the samples. Yep.
Excellent. Next question is from Timothy Pishkov. Do we need to do anything specific in STEM to get high-resolution images for thicker samples? I always thought that only TEM could get something decent if the sample is greater than 100 nanometers. Is it just the orientation of zone axis?
So with the STEM in particular, your margin for error certainly, well, I mean, the orientation, actually, I can go back here and show you this just so you can see it again. Oh, wait, no, I'm going the wrong way. Let me go back here. Okay, so this was what I showed you with the strontium titanate. As I'm tilting away from the zone axis. I don't know how thick this sample is. I want to say, maybe this is like a few tens of nanometers. So this is not, into the hundreds of nanometers. I do know experimentally, right? Because I showed that example, right, which is actually back here of the calcium lanthanum sulfide, right, of the high-res TEM versus the HAADF-STEM. Without question, alignment with the zone axis to get the best STEM image is probably the most critical part of this, especially when the sample gets a little bit on the thick side. But that's the same whether it's thick or thin, really, is having good zone axis alignment. The problem with high-res TEM, though, is that even if you do have good zone axis alignment, you're going to have a ton of problems from chromatic aberration, as well as Bragg scattering being suppressed as well. And that's just, it's not going to give you good lattice detail, right? And that's exactly what we're seeing here on the left is the effect of that. So, but if we switch to the HAADF, right, again, if we're well aligned with the zone axis, we can actually see some very good detail. This is actually sub angstrom.
Thank you, Nick. Next question just popped up from Satya Chaitanya Vadamanu. Based on your experience, are there any good STEM methods to differentiate carbides and steels? The different carbides I have showed showed similar DP and seabed patterns.
Oh, that's very interesting. So one of the things I would recommend, of course, is that imaging, right? So in this presentation, I only talked about imaging, right? But imaging often doesn't tell you the whole story with things. This was something that I talked about actually in my webinar back in May when I talked about essential techniques and I talked about STEM EDS mapping, right? And I talked about that being essential to provide information beyond what you can get just from imaging. So one thing I would suggest, of course, is if you're not getting the full picture just from your imaging, just from diffraction patterns, I would do some kind of analytical analysis as well. If that's EDS mapping or EELS mapping, something like that, to complement that, because that may also be what you need in order to help you delineate those. Again, I don't know how compositionally different the carbides are, but that would be something to consider. So I would suggest adding that. And again, if there's a lot of similarity between the images, without knowing any more specifics about what you're trying to compare, it's kind of tough to say. But that would be one thing I could suggest is make sure you have an analytical component to go with your imaging and diffraction component.
Thank you, Nick. Any more questions for Nick? Follow-up point from Satya is they are M23C6 and M6C type 4. If that gives any more context for you.
I'm not really sure what that means. So
Okay.
this might be I don't know, this might be from a metallurgy perspective. So I don't have a metallurgy background. So yeah, that doesn't give me any more additional information to kind of go on. So
Okay. Well, a separate question, unrelated. Qingtao Ku to everyone. STEM have a shallow focus depth, and if we change the focus, why does the STEM image get blurred instead of focusing on another atomic layer? In a normal atomic STO HAADF image, are the atoms in the image on the top surface of specimen?
okay, so that's a really good point to mention. So if I go back here, so this is really a question about depth of field. Okay, and this person is absolutely correct here. Let me make sure whoops, screen sharing has stopped as the window is closed. All right, let me go back here. I shouldn't have got out of presentation mode. Okay. Where are you? Okay, let me go back here. No, that's not what I'm looking for. Okay, I can use this here. Okay, so this semi-angle of convergence is ultimately what dictates the depth of field. Okay, so what happens, right, is as alpha gets bigger, my depth of field gets smaller. Okay, the depth of field gets smaller. So this is actually, believe it or not, this is something that people exploit intentionally when they have a very small depth of field. Like when you have, say, 20, 22, 25 millirad, they actually will exploit that to focus on specific depths within the material. Okay, so they will actually use that as a way to probe within a material to focus on a certain plane. Okay, as you know, if that angle is a lot smaller, it's about 10 millirad for a non-corrected tool. You're not doing that quite to the same degree. In terms of where you're actually focused, though, you know, it can depend on a few factors, right? So this is where actually, believe it or not, simulations kind of come in to help, right? So they kind of come in to help make sense of this, because I know there's been some simulation work that looked at the effect of what happens if I have like a damage layer on the surface, right? So what they actually determined is that if there's a damage layer on the surface, your optimal focus state is actually one where you are slightly under focused rather than being focused right on the surface, right? Because of the presence of the damage layer. So, you know, that's where, right, sometimes you need additional tools to help you make sense of what you're seeing, right? Generally speaking, though, you know, if we're talking about just atomic level detail, it's usually pretty obvious, right? When you're focused like right on the surface, because you're going to see really the sharpest contrast, right? Especially with HAADF-STEM, because you don't have the issue of contrast reversals with the focal state. So it's usually very obvious when you hit that sweet spot with the focus and you have the sharpest contrast. But again, though, right, depending on what I have with the sample, if I have a damage layer on the surface, if I don't have a damage layer, I might actually be focused, you know, not quite on the actual top surface. I might actually be focused a little bit differently. So yeah, it's a bit of a complicated answer, but definitely a good point to bring up.
Okay. We got some nice little follow-up questions on that one. Excuse me. Again, from Ching Tao Ku, in terms of magnetic domain mapping, is there any difference between Lorentz mode and DPC?
So Lorentz mode is simply a type of DPC. So let me go back to the end here. Sorry, I got a few animations. Yes, and I apologize if I didn't clarify that well enough. But yes, the idea is that Lorentz mode is simply a type of DPC where we have turned the objective lens off. Okay, so that's the only difference between Lorentz mode and DPC regular, right? DPC regular would be where the objective lens is still on. That would be usually when we're trying to do like atomic resolution work. If we are doing Lorentz TEM, though, I'll actually, let me go back here. We're typically going to use a setup here where my direct disk is just a little bit bigger than this inner rim. Okay, so we probably wouldn't magnify the direct disk to the degree that we would here. This would be more conducive for something like atomic res STEM work. If we were doing Lorentz STEM, we would have the direct disk a lot smaller. My semi-angle of convergence would also probably be a lot smaller as well. We probably would be having like single digit value for alpha, not having any overlap with the disks either. It's actually very interesting. I've actually seen this happen where the beam scans over a magnetic domain and you can literally see the direct disk like shift by quite a bit because of the domain structure there. So, and it's really cool to see that happen. And again, that's because we've turned off that internal magnetic field from the lens that we can do that. Okay, so hopefully that clarifies that.
Okay. And then this is from Rahu Agrawal. Which focusing should be preferred for STEM imaging? Changing specimen height or via changing OL strength?
All right, so that's another great question. So the general rule with that is assuming that you have your lens set to its proper optimal focus value, right? So there's going to be a proper optimal focus value when you're in STEM mode, right? That's the eccentric focus, okay? This is something I'm going to go over tomorrow at the demo. So I would encourage you to attend that so you can see that. So once you have the lens set to that, you want to do the majority of your focusing by adjusting Z. Okay, so you want to bring the sample into focus by moving it up or down, okay, first. Once you get it into rough focus, you can make small tweaks by adjusting the objective lens. The idea is that you don't want to defocus your objective lens by a lot, okay? So you want to keep that, there's a parameter called defocus, which you can see, and you're trying to keep that as small as you possibly can, okay? So if you do it right, you shouldn't have to deviate usually more than like a few tens of nanometers, if that. Usually I can do even better than that when I'm doing my STEM imaging. I am aided by, on our system, we have a piezo enhanced stage, which is really, really nice because that allows really fine positioning along the Z-axis. So we can use that. I think they claim that has like picometer sensitivity, but that is great to just bring the sample up and to be like really precisely focused just with the stage alone, and then we can fine tune the focusing from there with the lens. So that's the short answer is use the stage for most of the focusing, use the lens for any fine tuning after that.
Thank you, Nick. Any other questions for our speaker, Nick Radowski? We've got some accolades coming through in the chat. Thank you, Nick. Got it. Thank you, Nick.
You're welcome.
Anyone? Thanks, Nick. A lot more. All right, everyone. Hope most of you are showing up tomorrow for the demonstration. It's 2 o'clock Eastern time. If you haven't registered, you'll need to register separately for that one.